Okay, so here's another example that you might consider. So take a minute to see if you can address question 1. So would you predict that aluminum could dissolve into zinc or silver dissolve into zinc more favorably? Apply your Hume-Rothery rules to see if you can decide which one would dissolve more preferentially into zinc. Resume the video when you're ready. Okay, so hopefully you've had a chance to think about some of the rules. So if we're asking aluminum to dissolve into zinc, we could consider the radii. So the radii difference between aluminum and zinc, something like 0.1431 minus 0.1332. That gives 0.0099 divided through by the solvent. So in this case, the 0.1332. which is a percentage difference of about 7.4%. So clearly the radii condition for getting aluminum into zinc is satisfied. Okay, silver is very close in radius to aluminum, so I don't expect a major difference in the first Hume-Rothery rule, and so it will also, by radii arguments, favor dissolution into zinc. Second, we can look at the crystal structure. Well, both of the solutes that we're addressing are face-center cubic, and they're being asked to be hosted into a different lattice. So neither of them matches the lattice, so we don't have an argument for one being preferentially solubilized into zinc by that condition. Lastly, the electronegativity values. You can see here the zinc electronegativity value is 0.16, and we have that of aluminum being closer to that than the silver. So at this point, the electronegativity difference argument is favoring aluminum over silver. Considering valence values, so the zinc is a +2 versus the silver and aluminum being one oxidation number away from that in either direction. So silver +1 and aluminum +3. So we don't have an argument there for more one winning over the other. So based on the electronegativity arguments, the answer would be more aluminum would be expected to be included into zinc for that question. Okay, we'll just clean that up a bit. We can consider one more here. So the next question, why are palladium and platinum completely soluble in copper and allow for the formation of a substitutional solid solution? Again, you can pause the video once you've had a chance to consider our options. Okay, so thinking about the first rule, radii, you can see here that our radii are very closely matched. So these two radii are very close, certainly within 15%. So we have the radius argument favoring substitutional solid solutions of getting palladium into copper, I should say, up at the top. Sorry about that. Quite close values. As a quick check, you could take one. Again, we'll take the difference between the two, so 0.1387 minus the minus the the 0.1278. We should get something like 0.0127 divided through by the host radius, so divided through by the copper radius, 0.1278. And so you should get something about 10% difference between the platinum's radius and that of the copper. The value of palladium is even closer, so certainly less than that 10% difference. All three of these metals have the same lattice type, so that's favorable. Both the two metals in question have the same electronegativity difference, quite large, about 0.3. So that's working against the solid solution by substitution argument. And the valence values are matched to that of the copper. So we have three of our Hume-Rothery rules satisfied and only the electronegativity value difference not in favor. So again, for that reason, quite a lot in favor of getting these metals to mix. Okay, so just to help us quantify and describe these solutions a little better, we have, of course, the idea of expressing the mixture as far as weight percent or atomic percent. So weight percentage, of course, can be the mass of the solute divided by the mass of the total solution. So we see mass of solute as the numerator divided by the mass of the total. So this was both mass of solute and mass of solvent in the denominator. And of course, if we want to do percentage values, multiplied by 100%, and we've got our weight percent. Okay, similar ideas below. This time we're, of course, going to count by number of atoms. So if we are given only the mass information, we will need to transform the mass information into moles or into actual atom number. And so we will need atomic weight information. So that's reflected in this equation here, which is simply taking the solute as a numerator again, but first transforming any mass information into number of moles of the solute. And then again, the numerator or the denominator is going to be the number of moles of solute and solvent multiplied by 100% to give the atom percent value. And in the latter, actually counting by mole or by atom can be very useful for understanding things like some of the energetics involved in asking one atom to substitute for another, because often that is normalized per atom site or per atom solute rather than by the characteristics of having the mass, which is sort of the option up here. So counting by atom percent is often more useful when we think about energy for creating some of these substitutional solid solutions.